Imagine holding the entire universe in your hands. Every galaxy, every star, every planet, everything that has ever existed. Now remove 95% of it. That's not science fiction. That's modern cosmology. According to the best measurements we have, the universe is made of roughly 5% ordinary matter, 27% dark matter, and about 68% dark energy. That means everything we have ever seen, every star in every galaxy, every nebula, every planet, every atom in your body, all of it together makes up only 5% of reality. The remaining 95% of the universe is something we cannot see, something we cannot touch, and something we still don't fully understand. Dark matter does not emit light. Dark energy does not behave like any energy we know. Yet without them, galaxies should not exist, and the universe itself would behave completely differently. So what are they? Invisible substances filling the cosmos? Or signs that our understanding of gravity is incomplete? To answer that question, we need to start with one of the oldest mysteries in astronomy. In the early 20th century, astronomers began studying large collections of galaxies known as galaxy clusters. One of the most famous examples is the Coma cluster. This enormous structure contains thousands of galaxies bound together by gravity. In the 1930s, a Swiss astronomer named Fritz Zwicky began studying how galaxies inside this cluster were moving. He expected their motion to follow a simple rule. Gravity from all the visible matter should hold the cluster together. But when he measured the speeds of the galaxies, he discovered something shocking. They were moving far too fast. So fast, in fact, that the cluster should have flown apart billions of years ago. According to Newton's laws, the visible mass simply wasn't enough to keep everything bound together. Something else had to be there. Something massive. Something invisible. Zwicky called this missing mass dunkle materie, dark matter. At the time, most astronomers dismissed the idea. It sounded too strange, too speculative, and there was no direct evidence for it. For decades, the concept remained largely ignored. Until another astronomer noticed something equally strange happening much closer to home. In the 1970s, an American astronomer named Vera Rubin began studying the rotation of spiral galaxies. Her work focused on how stars move around the centers of galaxies. To understand why her discovery was so surprising, it helps to think about the solar system. In our solar system, planets closer to the sun orbit faster. In the innermost reaches, Mercury moves extremely quickly around the sun. Further out, our own Earth moves more slowly through its yearly orbit. And distant planets like Neptune take far longer to complete an orbit. This happens because gravity weakens with distance, so objects farther away move more slowly. Astronomers expected the same rule to apply to galaxies. Stars near the center should orbit quickly. Stars far from the center should move much more slowly. But when Rubin measured the rotation speeds of stars and galaxies, that's not what she found. Instead, something completely unexpected happened. Stars far from the center were moving just as fast as stars much closer in, sometimes even faster. This made no sense. If galaxies only contained the visible stars and gas we could see, the outer stars should drift away into space. Yet galaxies remained stable for billions of years. The only explanation was that galaxies must be surrounded by enormous halos of invisible matter. Matter we cannot see, but whose gravity we can detect. Dark matter. Since then, astronomers have found multiple lines of evidence pointing to the same conclusion. One of the most dramatic comes from a cosmic event known as the Bullet Cluster. This system formed when two massive galaxy clusters collided with each other at enormous speeds. During the collision, the hot gas inside the clusters slammed together and slowed down. But in this collision, something strange and unexpected happened. Most of the gravitational mass didn't slow down at all. It passed straight through the collision. Astronomers were able to map the distribution of mass using a phenomenon called gravitational lensing. Gravity bends light from distant galaxies, allowing scientists to see where the mass is located. And the results were astonishing. The visible matter ended up in one place, but most of the mass appeared somewhere else entirely, as if the majority of matter in the clusters were invisible and barely interacted with normal matter at all. This observation became one of the strongest pieces of evidence for dark matter. But what exactly could dark matter be? One possibility is that dark matter consists of entirely new kinds of particles. Among the most popular candidates are particles known as weakly interacting massive particles, often called WIMPs. These particles would have mass, meaning they produce gravity, but they would interact extremely weakly with normal matter, which is why we cannot see them. Experiments deep underground are currently searching for these particles, facilities shielded by kilometers of rock. Other scientists are searching for dark matter using particle accelerators, such as those operated by CERN. The hope is that collisions at extremely high energies might produce dark matter particles that briefly appear before disappearing again. Another possible candidate is a particle called the axion. Unlike WIMPs, axions would be incredibly light. If axions exist, they might behave less like particles and more like a subtle field permeating all of space. There is also the possibility that dark matter isn't made of particles at all. Some scientists have suggested that our understanding of gravity itself may be incomplete. One alternative theory is known as modified Newtonian dynamics. This idea proposes that gravity behaves differently when accelerations become extremely small. Interestingly, this theory can reproduce galaxy rotation curves surprisingly well, which means dark matter remains the leading explanation. For most of the 20th century, scientists believed the universe was expanding but gradually slowing down. But when astronomers studied distant exploding stars known as Type 1a supernova, they discovered something astonishing. These supernovae act like cosmic measuring sticks. By comparing how bright they appear, scientists can determine how far away they are. And by measuring their redshift, they can see how fast the universe was expanding. When researchers analyzed these measurements, they found something no one expected. The expansion of the universe is accelerating, not slowing down, accelerating. Something in the cosmos is pushing space itself apart. That mysterious influence is what we now call dark energy. One possible explanation traces back to an idea proposed by Albert Einstein. While developing general relativity, Einstein introduced a term called the cosmological constant. When physicists try to calculate the energy of empty space using quantum theory, they get a number that is catastrophically wrong, 10 to the power of 120. In one scenario, the universe continues expanding forever. Stars eventually burn out. The cosmos slowly fades into darkness. This fate is often called the Big Freeze. Another possibility is far more dramatic, the Big Rip. There is also the possibility that gravity might eventually reverse the expansion altogether, the Big Crunch. And that leaves us with one of the biggest mysteries in science. It is possible that dark matter exists as undiscovered particles. It is possible that dark energy is a property of empty space. Throughout history, whenever physics encountered contradictions like these, a scientific revolution followed. Newton once seemed complete, until Einstein revealed gravity is the curvature of space and time. Somewhere in that darkness may lie the next great breakthrough in physics.
The discovery that finally explains what 95% of the universe truly is. Until then, dark.